Section 13.4 is called Tangent Planes and Linear Approximation. And what we're going to be doing in this is very similar to what happened in Calc 1 when you first learned how to create tangent lines. Okay, so that's actually what we're going to start our discussion talking about, is that kind of an idea. Okay, what I'd like for you to do is to recall that a tangent line is a line very close to a curve near a specific point. Allowing us to approximate a value on the curve by using the tangent line. This was also called linear approximation. In section 3.1. In higher dimensions, this process is also possible using normal vectors. In 3D, or 3 dimensions in particular, we can create a plane let's say tangent plane here, and I'll shorten what I've written. A tangent plane to our curve. So the picture you want to sort of have in your mind or remember is that when you have a curve and you have a specific point on it, that tangent line right here is very, very close to the graph nearby the point. So if you wanted to find out what the value was on the curve and you didn't have the means to do so, maybe it's a very complicated curve. Obviously I drew a parabola, it's not a very complicated curve. But finding something, for instance, like the square root of 4.2 is not very easy, but finding the square root of 4 is very easy, right? So if you're dealing with a square root kind of function, linear approximation is a very good way to approximate something. Does everybody have everything written down? Okay. Theorem (4.1) says the following. Suppose that f of xy has continuous first partial derivatives at the point AB. A normal vector to the tangent plane to our curve z equals f of xy at AB is f sub x of AB, f sub y at AB, f, and then, sorry, negative 1. Furthermore, the equation of the tangent plane is z equals f of AB plus f sub x at AB times x minus a plus f sub y at AB times y minus b. So the first thing we're going to do is we're going to compare this to what you know about tangent lines to begin with. So what is the general equation for a line? Just plain old equation, 2 dimensions for a line. That's true. You're thinking standard form. I was thinking about like y equals form, just because I want to make it similar. What was it, Taylor?
Y equals a minus.
Yeah. I just want to compare what I've got here to what you're thinking. So this b right here is the y-intercept, right? What's wrong?
Yes, no, I was just,
Okay.
I said ax plus b equals y.
I thought you said
I was
ax
just
plus
backwards.
by equals, anyway. Okay, no worries. Yes, sorry. I'm sorry, I just heard wrong. All right, so this piece right here is the y-intercept, so to speak. It's a z-intercept is what we actually have. Because this is the z value. F of AB is just a z value. Okay? And then these pieces right here correlate to what's going on right here. Now, if we write this, and I'm going to write it in one other form that might even be a little more helpful for us. What if I write my form like this? Do you recognize that equation? It's the point-slope form of a line. So if you think about that from this sort of perspective, this piece right here is like my y0. It's the y-intercept, or not necessarily even the y-intercept, but it is a y value. And then this piece is slope. You can even say it this way. It's the slope at a particular point. All of that's the slope at a particular point, just like my m. And then this piece right here is x minus the x value. The problem is that we've got 3 dimensions going on in this particular form of this equation. So not only do we have the slope in the x direction, we also have the slope in the y direction, right there at the point AB, and we've got the y minus the y value, in this case b. So we've just sort of added a 3rd dimension. We didn't sort of, we really did add a 3rd dimension to what we've got going on. But the form of it actually looks quite similar. Okay? So what we're going to do next is we're going to actually use this formula, and we'll use the normal vector part as well up in here. You'll see how that works with an example. I lied. We're going to do something with normal lines first. Let me write the normal line part. I'm sorry. All right. So normal line. Also observe that the normal vector to a tangent plane is the line orthogonal to the plane passing through the point A, B, and f of AB, which is the z value we get out of using points A and the values for A and B for x and y. And is given by x equals A plus f sub x of AB times t, y equals B plus f sub y of AB times t, and z equals f of AB minus t. What's going on here? This should sort of draw you back into Calc 3 a little bit to something we studied there. You know what it should draw you into? How am I expressing this line? Huh? As a vector, yes. We also thought of it in a different thing too. Also as a vector, we thought about it as parametrically, right? Because it's got this extra parameter t involved. Do you see that t in there? Yep. So yes, it is as a vector with a parameter of t, right? T is our parameter. So you're imagining a curve, and so if you want to just think of a curved shape, so let's just think of a ball for the moment, okay? Tangent plane is going to be like a sheet of paper resting on the ball at a specific point, of course. And then the tangent plane points completely opposite of the ball, right? So the word orthogonal should also sort of resonate with you as something about like perpendicular. That's an idea that you're thinking of as sort of a three-dimensional perpendicular, or a more generalized word for perpendicular. All right, so this is called the normal line. To the surface at A, B, f of AB. All right, you guys ready? Do an example of this. So this is going to take this idea of partial derivatives we used in the last section and the idea of creating lines and then extending them into planes. All concepts that you've handled perfectly well before. So we're going to find equations of the tangent plane and normal line to the surface at the point. So we're going to be given a surface, we're going to be given a point. We're going to start with one that's relatively easy. Z equals e to the negative x squared minus y squared. And the point that we're going to be doing, we'll do this part A, is at the point 0, 0, 1. And that's part of what's going to make this clean, is that's a particularly nice point. All right, now notice back in terms on the last two slides where we talked about the tangent plane and the normal curve. Both of them require that we find f sub x and f sub y, right? So that's what we're going to do first. We're going to find f sub x and f sub y. So what is f sub x for e to the negative x squared minus 2y squared? Negative 2x e to the negative x squared minus y squared, right. And how about f sub y? Yeah, we would if it were addition or subtraction down on the sort of the baseline, but not in the exponent. Yeah.
Same thing, but -2.
Right, same thing, but it's negative 2y, e to the negative x squared minus y squared. Perfect. Now again, both of the forms that we were looking at talk about finding these partial derivatives at our specific point. I mean, just like when you worked with, tangent lines, the tangent line only gave you sort of a general equation for finding slope. To find the actual slope, you need to know the point where you were looking at. So we need to evaluate these at our point. So we want to evaluate f sub x at the point 0, 0, 1, or in our case, actually, 0, 0 is what we want to write down. The output is the 1. So if I plug in 0 for x and y, what happens to this particular partial? I get 0. And how about f sub y plugging in 0, 0? I get 0. So that's very clean, obviously. Lots of zeros going on there. And we can then find the tangent plane. So the tangent plane is z equals the third component of our xyz ordered pair, which was the number 1, right? We were given 0, 0, 1 as our point, plus, and we will write this down just so that you have it. I mean, plus 0, that's the slope f sub x, times x minus 0, plus the slope f sub y, which is 0, the partial f sub y, which is 0, times y minus 0. Or more cleanly, we could write that how? Yeah, that's just z equals 1. So if you think in 3 dimensions, this is really like a horizontal plane. We usually think of our z-axis going up and down, so this is like the ceiling, right? This is a horizontal plane at a height of z equals to 1. All right, we also have to do the normal line. So the normal line is x equals the x value, which is 0, plus the slope, f sub x, which is 0, times t. Y equals the y value, which is 0, plus the partial with respect to y, which is 0, times t. And then z equals the z value, which is 1, minus t. Oh, and well, let's write that down for a second, then I'll go back and clarify in a moment. Or, again, more cleanly, what would that look like? Right. So that's whatever it simplifies down to. I did want to make one comment I forgot to over here when we talked about the normal line. Why in the world does this become just minus t? All the other ones had f sub x or f sub y. Why does that have just the t? Why is it minus t? Do you know? Okay, take a look back over here when we were talking about the normal vector. The normal vector is found by taking the partials with respect to x and the partial with respect to y, and then -1 as the normal, the slope, basically, for your normal. Okay, so it's -1. So that's where it's coming from. We're multiplying it by that normal vector for your component t for the parameter. Okay, I wanted to do something with this particular equation that didn't have a whole bunch of zeros, so we are going to do a part B to this as well. So let's do part B, and let's do this at the point 1, 1, and e to the -2. Now we already have the same f, we already found f sub x and a f sub y, so we can just write those here again, or you can even not write them. I'll write them because I don't have them on my screen right now. Okay, so those were our first partials, and we need to find the f sub x partial at the value 1, 1. So if we're plugging in 1 for x and 1 for y, what does this become? I'll start you out. -2, because -2 times 1 is -2. What's next? E to the -2, right? Because 1 squared is 1 in both of those cases, so we've got -1 and -1, so -2. What about f sub y? should have written partial, or the number percent, f sub y at 1, 1. What will it be? Same thing, right, exactly. -2. There's a lot of symmetry going on in this particular function, right? All right, so we're going to do the tangent plane then. The tangent plane at 1, 1, e to the -2 is, all right, so we start out by writing z equals, and what do we write first? The output, the third value, right, in the ordered triple, so that's e to the -2. Plus, or in this case, we're actually going to end up with minus. We have the slope, or the first partial with respect to x, so that's -2e to the -2. And then what do I do? Right, I need to do times x minus 1. And then I need the partial with respect to y, so that's -2e to the -2. And then that will be multiplied by y minus 1. Is this going to simplify, you think?
I was making a joke.
No, not going to simplify. It looks like it probably will, doesn't it? Let's clean it up just a little bit here. So we have e to the -2. I have -2x e to the -2, and then plus 2e to the -2. -2e to the -2y, or -2y e to the -2, and then plus 2e to the -2. So what do we have? Hmm? 5e to the -2 minus 2x e to the -2. Keep going, Nathan. Very good. So this is our tangent plane. It looks and feels a little funny with those e's in there. You just need to keep remembering e's not a letter. E really is a number, and it's not a function either, right? It's not e to the x. It is e to a number. So this really is a numerical value. All right, we also need to find the normal line, right? So we need to do our normal line. The normal line is, so we do x equals the x value. What was the x value? Right? And then minus the slope at x, or the partial with respect to x, that was -2e to the -2, right? Times t. What is y going to equal? Fabulous. And then we have z. What's z? Right, e to the -2 and then minus t. So finding the normal line is not difficult, right? You're just taking the pieces you already did. I mean, it really is not another step in the process. It's just writing down pieces in a little bit different order. All right, I'm going to do another example. It's a little bit different directions. We're going to compute the linear approximation of the function at the given point. And we're going to do the function f of xy equals sine x cosine y. And we're going to do this at the point, right over here, at the point pi over 4. Now you might notice that right now we were just given the x and the y as the ordered pair of the input values here. We weren't told the output value like we were on the last problem. It really shouldn't concern us. We can find the output value, right? In fact, that's probably a pretty good first step to do, is to recognize that this really is a location in 3 dimensions. So let's find the corresponding z value that goes with this. So let's find out what is f of pi over 4, pi over 4. In other words, what is the sine of pi over 4, cosine of pi over 4. So each of those values are the same, right? What is the sine of pi over 4? Yes, radical 2 over 2. Same thing for cosine. So if you multiply those, you do in fact get 1/2, because you're going to get 2 over 4, which simplifies to 1/2. So this is in fact the ordered triple, if it helps you to think about it this way, of pi fourths, 1/2. Okay? Now, once we've done that, the linear approximation is exactly the same as finding a tangent plane. It's just got a different name. And that's all it is. And correspondingly, instead of writing z equals, because that's what we would write for the equation of plane, we're going to write L of x, y, because it's a linear approximation in terms of the variables x and y. Okay? But the formula is exactly the same. The first thing in our last formula is, what's the z value, right? Well, the z value here is 1/2. And then we haven't actually gotten to the point of being able to finish this, but I just want you to recognize what we're going to do next is we're going to find the first partial with respect to x, evaluated at our point in this particular case, which is pi over 4, times x minus, in this case, pi over 4. And then we're going to find the first partial with respect to y, again evaluated at pi over 4, and multiply that by y minus the y value, which is pi over 4. So there's nothing different that we're doing. We're just calling it L of x, y. And at the very beginning, we have to find the output value, the third part of the ordered triple, because it's not usually given to us when they present it in this way. Okay? So I'm actually going to slide this down. We're going to come back to it. And we're going to find the missing pieces, which are the first partials, right? So what is f sub x? Cosine, what did you say? I'm sorry.
Cosine y, cosine x.
Okay, or cosine x, cosine y, either way, yes. And here, let me move this as well. We'll find the first partial with respect to y. So what's the first partial with respect to y? Right, negative sine x, sine y. And now we're going to find each of these evaluated at the point we care about right now, which is pi over 4, pi over 4. So what is the cosine of pi over 4? We already did that. Square root of 2 over 2, and we've got it twice right here, right? So just like a moment ago, square root of 2 over 2 times square root of 2 over 2 is 1/2. Now f sub y is slightly different than that, evaluated at pi over 4. What's going to be different? Yeah, we're going to have a negative because there's a negative in the f sub y equation. So this is actually going to be negative 1/2. It's not too bad, right? So we can actually use that now in this linear approximation equation and evaluate with those particular points in here. So I have 1/2 plus, and then f sub x was 1/2 times x plus pi over 4. I'm sorry, minus, put that in there, minus pi over 4. And then I have minus 1/2 times y minus pi over 4. Now, if you'll notice when I distribute the 1/2 and the negative 1/2 through, this step and this step, one of them is 1/2 times negative pi over 4, the other one is negative 1/2 times negative pi over 4. Those add to 0, right? So in all honesty, those are going to cancel each other out. So this is really just going to end up being 1/2 plus, you can either write 1/2 x or x over 2. And then 1/2 y or minus y over 2. So that's our linear approximation. Now, notice I said this is the same as a tangent plane. And it is in 3 dimensions. But can you imagine what this would do if you generalized it to 4 dimensions? Yeah, you just have to add the next step on. So if we had 4 dimensions, like L of x, y, z, the first thing we need to know is we need to know the output of the L. So we need let's say that it is x, y, z. Often we'll use w as the 4th one. Then this value right here is the w value, right? Whatever that w value is. And then you'd need f sub x, and you need x minus the x value. And you'd need f sub y, and you'd need y minus the y value. And then you'd need f sub z and z minus the z value. And we could do this for a 5th dimension or 6th dimension. It just, you just add an additional piece onto the puzzle at the very end. I'm sort of oversimplifying the complexity of that. It means you have to find more partials, right? And that could be complicated with the functions you're given. But the process in general of the idea of what's happening is not any different. You're just adding another dimension to what's going on. Unfortunately, it's no longer a plane, right? You add a 4th dimension or a 5th dimension, you've got this different sort of a shape that we don't really have the ability to describe very well any longer. So it isn't really a tangent plane, but it is still a linear approximation. So we get more of a generalized statement by calling it that. All right, homework. This is page 852, and it is not very long. It's numbers 1, 3, 4, 7, 10, and 11, and then 39 and 40. These problems, 1 through 11, are going to look a lot like what I already did. Okay, the first 3 are going to actually say tangent planes and normal lines, and the next 3 are going to say linear approximation, which we all recognize is really the same question at this point. These 2 at the end, I'd like for you to take a look at, and we'll talk about those right now.